Welcome everybody, my name is János Sztakovics, this is my friend and colleague Tamás Hajdú. We are working together on eclipsing binaries on the University Department of Astronomy. And Gábor, previous speaker, has already spoken about the binaries and eclipsing binaries, so let's go. Okay, this slide, why use GPU? He also mentioned that we have a lot of eclipsing binaries, thousands of targets, and we have long observations. Kepler, for example, observed eclipsing binaries almost for 4 years, so we have a huge amount of data. And in this new era of observation of eclipsing binaries, we need a fast and automated processes to analyze the data and to make science as soon as possible. So the classification of eclipsing binaries, these were also mentioned by Gábor, so going on, physical parameters, orbital elements, which could be determined from the light curves, are the next, the orbital period, the eccentricity, and the omega, argument of pericenter, fractionality, and so on, a lot of other parameters, but we are now using and mentioning these parameters only. Eccentricity, just for repeating, if it's 0, it's the orbit is circular, and if the higher the E is, the stretch the orbit is. According to Kepler's second law, we can say that if the host star is near to the primary star, so it's in the pericenter, its orbital velocity is faster, is bigger, and if it's here in apocenter, it's slower. It's an important point. And the small omega, the argument of pericenter, is a kind of position angle of the orbit. It affects where the secondary eclipse will appear on the light curve according to the primary one. So according to this angle, we can see this kind of light curves. Okay, so I am working with these two parameters, the eccentricity and the argument of pericenter, because of the fact that the orbit of eclipsing binaries are evolving during their lifetime, because of the tidal forces between the companions. We think, the models say that the eclipsing binary form on eccentric orbits, and during their lifetime they became circular. And we think that the study of eccentricities provides us an opportunity to study these tidal forces, these tidal processes, and the timescales of the circulations.
Here comes a new topic, the R-C diagrams, which is good for, if you know the orbital period of the eclipsing binary, then we can calculate when will the next eclipse happens, so we have a kind of predictions, and also we can measure when the next eclipse happens, and with the difference of the two value gives the O-C diagram. This diagram can give us so much information about the system. For example, if the period has a kind of error, we can clarify it, or maybe there is a kind of a mass transfer between the elements, then we can catch it. And also we can find third bodies around the eclipsing binaries. It can be planets or another star as well. Motivation. So we are talking about hierarchical triple star systems if there is an eclipsing binary and far from them there is another star which perturbs this eclipsing binary. However, we are not able to detect directly the third star most of the time. If it makes eclipses, then we are able, but that's not the official way. How can we check that this component is belong to these systems or not? So, for example, there are double eclipsing binaries where there aren't any connection between the systems, just they are in one direction. So only the gravitational effect is measurable. So the third body perturbs the eclipsing binaries, and because of the finite speed of the light, the minima appear later or before we predict. So it will makes a kind of sinusoidal shape if there is a third body in the system, and we call this light travel time effect. So because the systems, the eclipsing binary is distance from us is changing, therefore we got a kind of sinusoidal shape. I think here is the red one is the primary, and the blue one is for the secondary minima O minus C diagram. Most of the binary stars have a third companion, especially if this eclipsing binary has a very short period. I'm thinking about around 3 days. So therefore, to find this third companion, it's essential to improve our stellar evolution models. And if we fit these O minus C diagrams, we can get information about the outer orbit's period, the eccentricity, and the separation of the binary and the third companion. So Gabor has mentioned Kepler and Kourou space telescope missions. Both of them was created to find exoplanets, but eclipsing binaries are not that much different from transiting exoplanets. Just there are 2 eclipses and the objects are much bigger. So the Kepler space telescope has found around 2,900 eclipsing binary. There is an official catalog for eclipsing binaries for Kepler, and we found around 1,500 eclipsing binaries in Kourou field. And there are also ground-based observations like optical gravitational lensing experience, OGLE, which also provide us a very long light curves. However, because it's ground-based observation, there are gaps in the light curve, so we have to work differently with ground-based observations.
Okay, so let's continue my part of this work. I work with detached systems. We could look that the detached systems have deep sharp minima, deep sharp eclipses. The deeper one is the primary eclipse, and the second one is the secondary. And we can well-define the beginnings and ends of the eclipses. And it's very good for us. Why? Because from the eclipse durations, we can calculate. So if we pick this point and this point, T1 and T4, these are called contact times. If we take the approximation of the primary and the secondary and combine them this way, we can get the value of E times eccentricity times sine omega. But if we go on and pick the displacement of the positions of the primary and the secondary eclipse, we can get E times cosine omega, and from these two, E sine and E cos omega, we can calculate eccentricity and omega, of course. We have a lot of in common in our work with Tamás. These steps are common for us. After downloading the data from the databases, we have to fold and bin the light curves. But before we could fold and bin them, we had to determine the orbital period of the binaries and how it is made. It's made by FFT or Loránd parallelogram methods. These two are better for semi-detached and contact binaries because of the sinus sensible form of the light curve. But we have another method, phase dispersion minimization (PDM) method, which is better for detached binaries and ground-based observations also. I want to talk about this PDM a little. Here's a flow diagram. So the input is the light curve of the eclipsing binary. We calculate the variance of the light curve, and we pick test periods. The higher the resolution, the higher the n becomes. And here's a loop, which we can work on GPU. And we fold with the light curves with all of the test periods. And what is folding light curve? Folding light curves with a period means that we modular divide the observation times of the light curve with the test period, and we get a folded light curve with phases between 0 and 1. And we divide this folded light curve to the bins. They can overlap also. And for these bins, we also calculate the variances and average them somehow. And if we divide the variance of the folded light curve with the test period and the light curve's original variance, we got a variable called theta. And we got thetas for all our test periods, and the correct period of the system becomes where the theta has a global minimum. Here's a PDM diagram. So here's the lowest point of the diagram. So this is the correct period of the eclipsing binary. Why folding and binning a light curve is important? We can get by this folded light curve an average picture of the eclipsing binary. The binning process smooths the light curve, of course, averaging by the averaging. Now outlier points are on the folded binned light curve, and small effects are deleted, and huge, bigger periodic signs are clearer. So working with the light curve, with this mean light curve is faster. We have less points, and we can work these folded light curves. Now, so how do we find the eccentricity of the detached system? At first, on the folded light curve, we have to find the primary and the secondary minima, fit the shape with a single function, and from the and from these fits we can determine the position and the duration of the eclipses, so we can calculate eccentricity and omega. And some further operations by arrays are also done on GPU to increase the speed of our algorithm. So here are my results. On the left panel we can see eclipsing binaries, detached eclipsing binaries from the Kepler sample. The blue one are for cold and the yellow one are for hot stars, hot systems. And this is a period and eccentricity distribution of the sample. And this is the same for the furrow. It's not so populated, but it's the same. And we made some statistics for representing our results. So further investigations, future space and ground-based missions are waiting for work with, and many thousand systems to be investigated in the future. And the more systems, the better statistics from the period eccentricity distributions we get, hopefully.
Okay. One thing we forgot to mention that we use GPU for that binning process, and it makes it 10 times faster. So I also use that for the binnet light curve, and to determine the shape of each eclipses, I mean the primary and the secondary eclipse. I use only polynomial template functions for each eclipses, and then I use a Legendre-Markov algorithm also on GPU to determine the O-C values. So if we use space missions data, the light curves are continuous, so the mid time of each eclipse can be determined easily. And most of the time we have a very short periodic eclipsing binaries, therefore there are more eclipses. It can be up to 2000, so therefore GPU is, it can be 100 times faster than CPU. But actually it depends on how much eclipse are in or light curves. In case of Ogle, we have a few problems. For example, there are huge gaps, and because it's a ground-based observation, the signal-to-noise ratio it's not that good. And against these things, I figured out to use one template function to fit the eclipses. I mean, for the primary and the secondary, there is only one polynomial. And in most of the cases, I used wider time range to collect those data. Luckily, it's not a problem for us, so we will get less O-C points than there are more eclipses, but it's not that much problem for wide hierarchical triple star systems. So in coral fields, we found 6 new triple star systems which has already published in Royal Astronomical Society in this year, and we are tested our new program with the Ogle's light curves, and we already found around 100 multiply system, and maybe there is a quadruple systems like here. There is a small sinusoidal shape with a bigger sinusoidal shape. Therefore, we are thinking that it can be a very interesting quadruple system. And thank you for your attention.
problems. Any questions? Did you by chance compare with Gábor simulation whether you can reconstruct all the parameters?
Not yet.
But is it in the plan, or it is so trivial that it is unnecessary and unimportant? Because there can be many noise, this different kind of structures of noises in the measurements. So and I guess you have no other baselines where you know exactly the parameters, or do you have from other observations binary systems where you know exactly what is the
yeah, I have eccentricities and these omega, small omega values compared with other papers, other results, and they are very, very good agreement. And with the simulations from measurements from radio velocities and similar simulations and as Gábor is preparing to do for lightcurves, so they are in a good agreement. Yeah. So we are planning to compare our results with Gábor too.
And any possible extensions to multiple star systems? How difficult is?
You mean?
When you have, for example, 3 stars in a system, maybe equally closely. So how? So that you might be
future plans, not yet.
Okay. Thank you very much.
Thank you.
Any more questions? Okay, then let's thank the speakers.